Okay, so today we're gonna do the second lecture on multimodal modeling. We're gonna have three this semester. And if you remember last time we talked about these vision language models or VLMs, and they can basically take in both text and images and produce text. Today we're actually gonna focus mostly on we're gonna focus on the things in the bottom category, and we're actually gonna think about this one here, which is how can we have a model that can produce both text and images? And of course, these can be kind of interleaved with each other. And then as a kind of spoiler, it's going to turn out to be a bit tricky to produce both text and images at like state-of-the-art quality. So then in the third lecture, we'll talk about models that really just focus on producing images. And at least at the current state of time, we don't really have a single kind of unified solution. We're going to use techniques based on like diffusion to produce really good images. And as of now, to produce really good text, the best models are based on autoregression. Okay, but hopefully you'll have some overview of different modeling paradigms and a lot of kind of interesting ideas, and you'll be able to read about some more recent methods after these lectures. Okay, so here's a now kind of outdated screenshot. So this is from what ChatGPT 4.0, which is or GPT 4.0, which is the old version. But here the idea is, I said generate a framed picture of Pittsburgh in an impressionist style, and it was able to produce this picture. And of course, ChatGPT can produce text. So we're not necessarily going to go into the techniques that ChatGPT uses because we don't know exactly what they're using. But here's just showing you, one use case for producing an image and also, wanting to have a kind of conversation in text with the model. Um, so first we're going to go, since we're going to talk about not just autoregressive models, especially in this lecture and the next one. First, I'm just going to go over a broad overview of some of the major paradigms for generative modeling, and that'll kind of give us some, footing for some things that we'll talk about today. Then we'll actually try to directly use the techniques that we've been using to generate text and just basically treat an image as, tokens. So what if you just learn to kind of like predict the next pixel instead of predicting the next token? So kind of interesting idea, and we'll see maybe some of the limits of that or kind of what we run into. And then what you do in practice is this can run into some issues. So people have also tried kind of coming up with a more compressed representation of images. And unlike the previous lecture, now the model is not just going to take in these kind of compressed image tokens, it's also going to have to produce the tokens because you want to generate an image. And so the techniques are actually going to be slightly different than the ones that we saw in the previous lecture. Okay, so first, just introducing this idea again of a generative model. So we have some data distribution. We want to train some model, and it could be this probabilistic model. And then we want to generate things with it. And you can think of this as being, if you have this probability distribution, kind of sampling from the distribution. Okay, and in especially these three lectures, we're not just talking about text, we're also talking about things like images. And so we have to look at, not just these autoregressive models, we have to think about what is kind of the best tool for modeling, a variety of types of data. This is already getting slightly outdated. Maybe there's a fifth category, but here's kind of four different paradigms that have been developed over the years, especially in the context of deep learning. So at the top here we have the autoregressive models. These have been the ones that we've been using with text and are kind of state of the art for text. But there's other things you can do. So there's variational autoencoders, generative adversarial networks, and diffusion. And then maybe the fifth one is called flow-based models, which is kind of like slightly more general than diffusion. Okay, so we'll go through, I guess, actually the details of all four of these in both this lecture and the next lecture. So the purpose of this slide isn't to, for you to understand all the details of these. It's just kind of a roadmap of where we're going. But if we kind of keep doing a quick kind of overview to get the key intuition behind these different paradigms, let's just look at a few kind of quick examples. So again, autoregressive models kind of break things down into this like, multiple steps of prediction. And in some sense, if you have a variable which is multiple dimensions, or you have this like joint distribution, then they're basically generating kind of one dimension at a time, given the previous ones, according to some ordering. Okay, so with text, maybe there's this natural like left to right ordering, and you can break things down into tokens. So maybe we can think about, for other types of data like images, doing something similar. Maybe you could have, this is actually called raster scan order, which is basically like left to right, top to bottom. So we'll actually talk about this in a bit more detail, but maybe you could try to build an autoregressive model. Okay, variational autoencoders, if we kind of just look at the picture, then it's clearly doing something different. So again, we're going to go into more detail on this later, but here you have this notion of, well, first of all, you have two different models. You have this encoder and you have this decoder. And then you have this idea of this latent space in the middle, which is called Z. Okay, and so the broad idea that these are going to try to achieve is we're going to have this encoder, which takes in images or data and maps it into the latent space. Then we're going to have the decoder, which goes from the latent space and produces something in the data space. Okay, and so the idea is, let's say that our latent space is kind of structured in some way, like maybe it's structured like a standard Gaussian. Then we can generate data by just, in the case of a Gaussian, you just like randomly sample something from a Gaussian distribution, and then you can pass it through your decoder and you get something in the data space. So again, I'll go into a little bit more detail on this, but here you can just see that it's kind of different from the autoregressive model. Okay, generative adversarial networks is also something different. So here they kind of come up with this maybe like two-player game, and it's kind of clever. And so now you have this discriminator and you have a generator. Okay, so the job of the discriminator is, let's look at what it's doing. So it's getting both real, it can get a real image or it can get a kind of fake image, which was generated by the generator. And so the discriminator's task is to detect whether this input is real or fake. Okay, then the generator's task is going to be learn to generate images that the discriminator thinks are real. Okay, so you could see that like if your discriminator gets really good, then that means if it says that something is real, then it must be like a really, realistic image. So then you can basically use that as a signal to train the generator to like produce realistic data or realistic images. So again, that's the kind of high level idea based on this kind of two-player game if you want. And then diffusion, so we'll go over this. We'll have a whole lecture on it on Tuesday. Here you could again see that the idea is kind of something new. So here now we're going to start with this data, and we're basically going to slowly add noise to it across multiple steps, and we eventually arrive at something which is just pure noise. Now the learning problem is going to be, can you basically learn to reverse this process? So can you learn to start with, let's say, noise, and then across multiple steps, slowly denoise it and produce something in the data space. Okay, now if you think deeply, maybe these are actually related and you can relate all of them. But I'm just showing you that, they're kind of different paradigms, and they've kind of gradually been developed over the years. Okay, so first, as I mentioned, we're not going to go over all of generative models or all of multimodal or all of you know, yeah, multimodal machine learning. There's a course for that. here we're going to restrict to kind of things that we've been interested in and maybe think about like how do we modify what we've done so far in order to achieve what we want. Again, achieve what we want is we want a model to produce both images and both text and text. Okay, well, here's maybe what the picture would look like, right? We have this transformer. It takes in these vectors and it basically produces vectors and then ultimately produces some output. So in the case of text again, you have your tokens that are both input and output. So what if we came up with some way of, tokenizing an image and then producing tokens that you could then turn into an image? Then we'd basically be done. We could just use all the same techniques that we've been using, and we can produce both text and images. Okay, so the key thing here is we're going to need an image tokenizer, which we talked about in the last lecture, but now we're going to need this detokenizer. So if the model produces some tokens, we need to be able to, easily turn it into an actual image. Okay, so this is going to be the goal, and then we're going to think about maybe how to do it. So the first attempt is we're going to not do anything special. And in some sense, we could treat the tokenizer as just the tokens are individual pixels. And then we could just have the model, generate the pixels, and then you don't need a detokenizer. You have an image if it's just generating pixels. Then the second thing we're going to look at, as I mentioned before, is you could try, not generating individual pixels. You could try to kind of like learn this tokenizer. So we're going to talk about some techniques for doing that. Okay, so first we could consider, just treating the image as a sequence of pixels and basically learn a language model over these pixel sequences. Okay, so what you can do, again, you have the image, which is, 3 dimensions, height, width, and these channels. You could just flatten it all into this long sequence. And then each position might be, a number within some finite set, like 1 to 256 for the different pixel values. Okay, so you really can treat one of these images as, just the string, and actually the vocab size is pretty small. It's just, 256 possible tokens. Okay, now we can convert a, big data set into sequences and then just train a language model. So I'm going over this pretty quickly because nothing is changing from what we've talked about. Now instead of text tokens, you just have these kind of pixel sequences or the tokens are pixels. Okay, then we learn the language model with maximum likelihood. So this has actually been tried in various forms over the years. So here was a early work called Pixel RNN. So here they weren't using transformers, they were using RNNs. And you can see that, so what it's doing is, now you train the model and now you can basically prompt it with part of an image. And maybe the task is you try to complete the image and then somehow evaluate it. Okay, so here is showing you some examples. And I don't know, like the images are pretty small and maybe it's a bit blurry, but certainly it's learned something, right? It's not completely random and it has kind of learned some structure of these images. So this was the kind of early work, and then do I have it on here? Oh, so then I think the same authors then used a convolutional architecture. So there's like pixel CNN, and then they kept, trying to improve it. Then the transformers came along. So here's an example called image transformer. And again, they're trying to use the same idea of basically learning this autoregressive model. So here you can see like full images that it produces or this kind of completion task, right? Mhm.
So is this a little bit congruent to what was going on with like BERT at the same time with the masked, with the language masking? So they just did the same idea, but more with images where they took parts out and got trained.
Yeah, so here this is so I guess BERT would be you're removing kind of random positions in the image. But this is just going from left to right in some sense, except now the order is, top to, yeah. Um, so with BERT, again, you have to think about like how would you actually generate? Here you have this consistent generation order, so you can just generate from, top to bottom, left to right. Um, Also, OpenAI tried this, so they had something called Image GPT. So they had this paper, generative pre-training from pixels, and actually in this paper, to actually answer this question, in their paper they weren't doing image generation. They were basically just trying to learn representations, and then here like fine-tune a model for classification or yeah, fine-tune a model for something like classification. So there they actually tried both autoregressive and this BERT style pre-training, and then they just see like, can we learn good representations? But then they do have this blog post where they actually, um, I guess it was the same team or something. I don't really know, but here you could see they're actually generating. So they basically train this model to um, predicting kind of pixel space. So, what are some things that you run into with this? So first of all, a big challenge is the sequence length, right? So, if you think about like a really large image and or an image with 1,000 by 1,000, and it has three different channels, then that's 3 million tokens if each if you really are predicting each pixel. Um, and so now if you imagine having like video, maybe you have like a sequence of images, it's not clear. Uh, I mean, at least the question comes like, can you do something which is more efficient or has a kind of more compact representation? And so if you look at some of these papers, like the image transformer, for instance, they would typically involve some modification to be more memory efficient. So this might be from the image transformer where they're modifying the attention. And so you do have some trade-off, in the model architecture. And just in general, you have to deal with this kind of long context length somehow. Mhm.
Are you aware if somebody have tried maybe stacking models on top of each other to try to avoid like that limit of token output? So say like I generated one part with one model, and then
Mhm.
another model takes that generated part and expand it more and more until you reach the
Yeah,
token length
yeah.
that you wanted.
Yeah, so like generating at multiple resolutions or something
Right.
like that. Yeah. It might have been tried. Yeah, I'm actually not sure. It probably has. Yeah, I guess here we're just considering like an extreme of yeah, like what happens if you do maybe the simplest thing. So that's gonna be a challenge. And then another is maybe it's harder to pin down, but I think it's like gives you good intuition, which is like, maybe image data is actually slightly different than text data in the sense that like each pixel might carry relatively little semantic information. Whereas tokens, like word tokens, they, each token kind of serves a purpose. Maybe it's an article and it tells you something about the grammatical structure, or it's like someone's name and there's like a lot of information packed into a single token. But in order to like show that a dog is in an image, then you really have to look at a lot of different pixels and there's kind of like dependencies between them. Um, and so as a result, you might kind of need uh, a lot of data. So people have kept looking into this, and here's just one example. This is from November 2025, and it's from a group at Google. And they were basically just trying to see like let's try to make scaling laws for doing this autoregressive modeling of images. And they have some interesting findings. So first of all, up here you could see kind of language tokens versus these pixels, and it's looking at the optimal number of um, tokens per parameter. And so what it's basically saying is you need per parameter in the model, you need a lot more tokens per parameter for images. Possibly because there's a lot less, intuitively, there's a lot less maybe like information in a given pixel. But they did find that, as you scale up compute, the the models were getting better. So here you see this is in terms of classification performance, like using the representations. And then this lower is better. This is looking at the generative performance. And then the this is looking at the loss. So here you have loss, and then you can see the other things visualized. And they don't perfectly correlate, but at least they're, somewhat correlated. So I think one thing is they said like, oh, maybe in the future, if you actually do spend a lot of compute, and if the scaling laws continue, then this could be promising, although it might be a kind of computationally expensive way to learn this generative model. Okay, so that's the pixel modeling. So now we're going to think about trying to do something slightly different, which is like instead of having pixels as the tokens, we're going to have these kind of more compressed tokens, if you want. And this is actually going to lead to different trade-offs. So we're going to run into kind of different issues with this. Maybe let me pause for questions if anyone had any. Okay, cool. So yeah, now the idea is we want to somehow learn this like tokenizer and detokenizer and kind of represent these images more compactly. So for example, now let's say that we have we're going to set for our tokenizer, let's say you can have 8,000 tokens, and now I want to represent an image. Instead of 3 million tokens, I want to just use 1,000 tokens to represent the image. Okay, this will be much smaller context length, much more memory efficient, things like that. So the approach that we'll look at is something called vector quantized VAE, and this was used in a lot of like attempts at kind of doing this, and then or not surprisingly, but it shows up in some recent attempts that we'll look at to kind of train these multimodal models at a large scale. So there's a model called Chameleon that was trained by Meta, and it used something similar to the approach that I'll introduce here. Okay, it's also a nice excuse to kind of introduce and learn about variational autoencoders. So you saw VAE in the name. So here's again the picture that we saw, and the kind of challenge here that these will try to solve is basically learn to compress an image into this latent space, and then learn to kind of decompress it with this decoding step. So first, let's think about this just for kind of continuous data, like images, and then we'll see how we can use this to come up with this kind of tokenizer. So it'll be discrete data. Um, oh, okay. So first, so again, how do you use these VAEs to like generate things? So let's say that we learn this encoder, and we're going to try to ensure that this latent space is kind of well structured. In particular, we want the latent space to look like a normal Gaussian. Then if you do that successfully, then to like generate images or generate data, you can just sample from a standard Gaussian, and then you can pass it through the decoder, and that will give you, an image or the data that you're modeling. Um, and this is kind of the standard version. Of course, you could think about, modifying things. So let's take a look at how you do this, and then we'll see how to build the discrete version. So first, there's going to be this notion of latent variables. So we're going to basically assume that data is generated as follows. Again, first you sample this latent variable, z, from a prior distribution. And so the prior will be, like a standard Gaussian distribution. Then we turn it into data with a decoder. And then our encoder, again, it's just kind of assigning terms to these things. We'll map data into a latent variable. So here we can just look at the kind of objective, and then I'll go through the derivation just so that you've seen it. But we can kind of look at the result of the derivation first. And so the way that you train this kind of breaks down into two different terms, and they're kind of interpretable. So first we want to have a loss term for kind of reconstructing or for the decoder. Okay, so here we're going to have a loss term that says, maximize the probability or minimize negative log probability of the data given some latent variable. So that's going to train our decoder again to basically reconstruct data given some latent variable. Then we're going to want to produce latent variables and again kind of keep them well behaved or keep them close to this prior distribution, which will be a Gaussian. Okay, so then again, if you learn to do that successfully, now you can take the encoder, it can encode some data, and you can also kind of sample from the model by just sampling from a normal Gaussian and then passing it to the decoder. Okay, so you'll have these two different terms in the loss, the reconstruction term, and then this one you might call regularization, and this will be a KL divergence. Um, so yeah, here's just writing it as a final loss. So what we're going to do is we're going to have some data, right? And then what you have to do is when you're training the model, you want to produce some latent variable with the encoder, and then you want to apply your reconstruction loss to basically reconstruct the data given the latent variable from your encoder. Then over here you have this regularization term, and here it's going to be a KL divergence. And then I guess I'm not going through all the details, but you can basically set this up so that they're both Gaussians, and then you can just have a kind of closed form expression for this. Okay, as I mentioned, the purpose isn't to learn all the details, but maybe this idea of these two loss terms is kind of interesting and good to know about. Maybe this is one detail, but it's another interesting thing. And then especially if you read the paper or try to train one of these yourself, you'll see this in the code or have to think about it, which is like here we have this expectation and the model parameters that you're learning are part of the expectation. So what you have to do is what's called reparameterization to make things differentiable. So again, the issue is that we want to sample from our encoder and then pass that to the decoder and backpropagate. And so the sampling operation isn't going to be differentiable. But then you could basically do this trick of reparameterizing. So you could basically view this sampling operation as something you just do from a standard distribution like a Gaussian. And then you could view your encoder as being this like deterministic transformation of the random noise. Okay, so if you haven't seen this before, you'd probably need to look at some more details to really get at what I'm talking about. But basically, this is a common trick, and it's necessary in the VAE to basically train it with backpropagation. But it is possible to, make everything differentiable. And so, there's nothing, you can basically train the VAE with backpropagation. Okay, so one more thing that I wanted to introduce with the VAEs, because we'll see it actually when we talk about diffusion, and you'll see it when you read about generative models, is called the elbow or evidence lower bound. So basically, like I gave you this loss, right? And I said, here are the two different terms, and they're kind of intuitive. Um, but can we actually, motivate or derive this loss from something else or something maybe more principled? So you can using this idea called evidence lower bound. And so we could basically start with the same goal that we had with the text models, with the autoregressive models, which is maximizing the likelihood. Okay, I guess it's kind of small. So let's say that we start with the log likelihood of our model. Well, now this model had this assumption, right, that we had a latent variable. And so what we actually have is this joint distribution over both the data and the latent variable. And so if you wanted to compute the log likelihood and then try maximizing it somehow, you would actually have to marginalize out this latent variable. Okay, so that's what this is saying here. It's saying that you're like summing over or in continuous space integrating out this latent variable. Now what happens is if you think about like this z is this high dimensional vector, then actually doing this integration isn't really tractable. So you have to uh, kind of deal with that somehow. So we can do some kind of clever manipulations and then end up with this loss function that we can optimize with backpropagation. Okay, so first of all, what you can do is this trick. Anyone know what this is called here? Okay, so this is called importance sampling. So the idea is you can basically introduce some other distribution, and it's going to turn out to be our encoder. And then you can basically just multiply by one, right? So it's like Q of Z over Q of Z. That's just one. So you can just introduce it into this equation. And then now, just using the definition of expectation, now we have this expectation, which is over this new distribution that we just introduced called Q. Okay, so this is a trick you'll see come up in machine learning in various areas called importance sampling or um, yeah, introducing this kind of proposal distribution. Um, Now here what we're doing is we're swapping this expectation and the log. So now you have expectation of log. Anyone know what this is called? So this is called Jensen's inequality. So this is just like this inequality. You might see it in convex optimization or in probability. And so if you have a convex or concave function, then one's a less than, one's a greater than based on whether it's convex or concave, and it allows you to basically swap these. But now we have this inequality. So we're no longer now it's going to be an inequality. Yeah. Okay, so now you can just kind of manipulate these logs and this distribution. So here we have a joint distribution. You could break it down into this conditional times P of x given z times P of z. And then you can just, uh, reorganize the logarithms. And now you get these things. And now if you take a look at this, this is actually the negative. This is the KL divergence. And then this is the reconstruction term that we saw before. Okay, so this is exactly the loss on the previous slide, or the negation of it. Okay, so what you can think about this doing is it's basically this lower bound on the log probability. Okay, so as we as we optimize, we're getting we're making the bound smaller and smaller. And you can see the relationship with kind of ideas that we were talking about before, which is maximizing the likelihood. Now we have to deal with this latent variable, so we end up with this, which is called the evidence lower bound. Evidence is some kind of Bayesian terminology for the uh, log probability or the data distribution. Okay, so you see this come up, and then when we talk about diffusion, they'll run into this again, and they'll have to come up with some way and come up with this evidence lower bound to derive a training procedure. So it's good to at least have seen this. Okay, so let's look at some maybe like images and some results. So this is from the original VAE paper, and yeah, you can get this kind of cool kind of functionality. So what this is showing is you can go over your latent space, right? So these will be like this continuous vectors in your latent space. And then you can say like, okay, what is the latent vector? I'm going to encode the number 6. So I'm going to have an image of the number 6. I'm going to encode it. And I'm going to encode the number 1 using my encoder. Then you could basically, in latent space, kind of interpolate, right? So you can get now new vectors. So you can get one vector, which is like halfway between 6 and 1. And then you can pass that to the decoder. And you could see that it actually has this kind of, you can do this kind of interpolation in latent space. So kind of interesting. And then you can do the same thing with, you know, any type of data you're modeling, including like human faces. Um, okay, and so VAEs is, turned into a whole research area, and this is just a standard VAE. There was hundreds, probably thousands of papers about them. So it's a kind of big topic, but at least now we can think about, okay, this is all in continuous space and with images. Does this actually help us for our goal, which is like tokenizing and de-tokenizing images? Well, if you think about it, like maybe this tokenizer is something like the encoder in a VAE, and maybe the detokenizer is like the decoder in a VAE. And that's exactly what we're going to try to do. We're basically going to try to, instead of having a continuous latent space, have a discrete latent space. Okay, so now your encoder can give you these discrete numbers or discrete tokens. And your decoder can basically go from a sequence of these discrete values back to your data space. So this is going to be the kind of trick, and then you can use this to then, have a language model that then produces these tokens and as a result can produce images. So the challenge is that, when you work with discrete data, things are maybe less nice in the sense that like it's going to be more difficult to get gradients and you kind of have to get clever. So this is a method called VQ-VAE or vector quantize VAE that tries to do this. Okay, so again, we have an encoder and decoder, and and let's look at what is here. And so again, our encoder is going to start off by going from our data and turning it into some continuous vector. But now we want to quantize. So we want to turn the continuous thing into something discrete. So the way we're going to do this is we're going to basically have what's called this code book. So the code book is going to be some finite set of vectors. Here it's showing 8, but this could be, it's basically like your vocab size, right? And you're going to basically compare your encoder output to each one of these codebook vectors and basically find the nearest neighbor. Okay, so we're going to find the nearest neighbor. And so in this case, the nearest neighbor is the vector 5. And so now we basically encoded, say, this image or this part of this image as the number 5 in this example. Okay, and this is just writing out the equations for doing kind of nearest neighbor lookup. And so what you can view this as is your model's giving you this like uh, distribution where all of its mass is over this single vector. Then you could try to pass this to your decoder, and now it has to reconstruct an image given this vector corresponding to 5. So the question is, yeah, how do you train this model? So first of all, you have to train this encoder. You probably, have to come up with some way of updating these codebook vectors. and then you have to train the decoder. So here's the kind of loss function that they have, and now it has three different parts. So first of all, you're going to have this reconstruction term, and this actually looks pretty similar, right, to the original VAE. Now you just have these vectors that have been kind of selected from this codebook, and then you know reconstruct your data. Here you have two different terms, and they're basically focused on these code vectors. So what this one is saying is, okay, given the output of your encoder, I want to make the codebook embedding that was selected for it kind of close to the output of the encoder. So this SG means stop gradient. So what it's basically doing is it's saying, okay, the output of the encoder is going to basically be the target and then the prediction target, right? And then this embedding is going to be kind of optimized so that it's close to the encoder output. Then you can think about the other extreme, which is like you don't want the encoder to just kind of do whatever it wants. You know, it could just produce an embedding anywhere in latent space. Instead, you want to make it kind of produce things that are close to some codebook embedding. So now you have the kind of opposite term, which is we're going to treat the codebook embedding that's selected as the target and make our encoder outputs kind of closer to that embedding. So those are the kind of the three terms. And then the one other thing you have to deal with is, again, the selection operation is not differentiable. So in order to use backpropagation, what they do here is use what's called the straight through gradient estimator. Okay, and so this is basically kind of naive estimate of the gradient. It's basically saying, you know, you're doing backpropagation, and we're basically going to kind of like skip this operation in the sense that you just like copy the gradient and use it as the gradient for then backpropagating through your encoder. Okay, so I'm not going to go into like too much detail on this straight through gradient estimator. I'm like writing an equation for it. But this is kind of the trick they have to do. And again, you run into this issue whenever you're working with discrete data. You usually run into some issue of like, how do you get a gradient because of some discrete operation? Um, so then the question is like, do you just use a single vector or a single codebook entry to represent a whole image? The answer is no. So what you can do is you could have, you know, multiple vectors. So here the latent vectors are kind of structured according to this, you know, 2D structure. So what it's saying is, you know, for each one of these patches, you're going to do a separate lookup operation, right? And so at the end of the day, you're going to have multiple numbers kind of corresponding to an image, and then each one of those numbers is going to be one of these lookup vectors. Okay, so you can see here in this position, what codebook vector 3 was found was selected here 53. Okay, then you could pass this to your decoder. And so you can see now here the idea, which is if we flatten all of these numbers, now you have basically a sequence that can represent your image. And let's say that your model produced this you know, sequence of numbers, then you can keep around these codebook vectors and basically then pass it to your decoder and it can produce an image. Okay, any questions about this? Have you been kind of following the argument and the technique here? Mhm.
Is the embedding space on this slide the same as the loading space that was shown earlier?
Yeah. So now we basically, I guess there's two ways to view it. So now you can view the latent space as being either these discrete numbers. So in some sense, this image is being encoded as just this matrix of discrete numbers. But those discrete numbers have this one-to-one mapping with yeah, these embedding vectors. So I guess yes. Yeah. Hmm.
For the decoder, would it make sense if you were trying to do a classifier to switch that out with like a classification head and still use this paradigm?
Mm. So you'd have to your objective would definitely change, right? Because now you're no longer reconstructing data. And so I guess it would be a bit different. What you could do is you could do all this training and learn an encoder and a decoder. Then you could just learn a classifier on the latent representations. Yeah. And that's actually something common to do. But the objective is basically the reconstruction objective is kind of important because it'll force the encoder to learn a kind of good compression of the data into the latent space.
I guess the other thing I was thinking of was instead of image to image, given the latent representation, could that be reused for, say, like text to image or image to text and try to borrow the same like latent understanding?
Can you say that one more time? Yeah.
And catch you later.
Okay.
Yeah.
Yeah. I mean, in general, these could be different types of data, and then you just have to, I'd have to think about the specific case you're talking about, but especially with text, you have to make sure things are differentiable and that you can get gradients. And then you also want to make sure that the there's not too many independence assumptions being introduced. So here it's basically saying that, given this latent vector, what these models typically do is they'll just predict each pixel kind of independently given the latent vector. And sometimes for text, those conditional independencies are just too strong, so it actually gets difficult. Mhm.
Is the expressivity of the VQ-VAE comes from the number of tokens and the different levels that we have? Because like
Yep.
if we think about it, if we only output one vector, we will be bounded by the number of vectors in the code.
Mhm.
But as we increase the levels, the number of choices increases exponentially.
Mhm. Yeah, so this is going to be on the limitation slide. So this is going to be a limitation of this. And when you think about it, you have these extremely, high dimensional images, and we're basically trying to represent them as, a sequence of 1,000 tokens, and you have maybe like 1,000 options for each token. And so the latent space is much smaller than the data space. Um, so you're gonna have to hope that your images really lie on some, really low dimensional manifold or something like that. But in practice, you're gonna see some loss of information, especially like the fine-grained details of the image. Yeah. So there's actually a code example. So if you're curious about like exactly or one way to implement this, you can take a look. And it basically uses this data set called MNIST. It's like the simplest data set. And then here you can look at the code indices that end up being used for these different positions. So it's kind of interesting. It basically learns to learn this kind of blank space token. Um, because the decoder then has a pretty trivial job if it's really just empty space. And in these simple images, you can get, probably pretty good reconstruction, even with this kind of discrete code book. Um, so then here's a more kind of real world example. So if you've heard of like Dolly from OpenAI, there's Dolly, Dolly 2, Dolly 3. Um, So before everything turned into ChatGPT, this was like the separate model that OpenAI had for uh, generating image given some text prompt. And this was the first version. And so the first version used this technique that I'm talking about. And again, this is when they had things publicly available. So you can actually download their encoder and decoder. So this is just showing you, you start off with an image, and then you're getting these kind of discrete tokens corresponding to the image. And then here's reconstructing it. And you can see that it's pretty good. Yeah, if you really look, it's getting a bit fuzzy, right? It's not as sharp as the original image, so it's maybe dropping some of the fine-grained details. Mhm.
For this version of Bully, there's no like text involved.
We'll get to that in a second, yeah. So there'll be text, which is like the prompt. So the prompt might be image of a penguin in snow. Yeah.
Have you run this like tokenizer like let's say like a million times or like 1,000 times? Like, will the image eventually degrade to like noise or
Hmm. Say that again.
if you like sort of tokenize it and then like like reconstruct it
Mhm.
over like 100 times, let's say, will like
Oh, I see.
eventually become like just pure noise as because of
That's a good question. Yeah. So it depends on the encoder. So that's actually an interesting question. So yeah, I guess if the encoder hasn't been trained on its own um, images that are decoded, then it might not know how to encode these like artificial images well, and maybe it does kind of degrade. But I'm actually not sure about the answer.
pretty opposite. Maybe the thing that matters
Hmm.
comes to the front and stays, and everything else goes.
Yeah, exactly. It could, maybe it actually can encode its own images pretty well. But um, yeah, I'm not sure what would happen in practice. It's a good question. Okay, I know we're going through like a lot of methods and each one's in like a different paradigm. But so here is again just showing a similar thing. So instead of using VAEs, so people were trying to kind of improve this idea. So people also looked into using GANs to again do this codebook idea. Um, Let me see what details I have here. Okay, so I'll briefly talk about this, but so this was a paper that, got a lot of citations called VQ-GAN. And this will be actually the tokenizer and detokenizer that's used in the meta paper that I'll mention at the very end. And so the interesting thing is here they actually do what I'm talking about. So before talking about the GANs, here again, you have some image, you encode it, and you get these numbers. And then up here, you can see exactly what I've been getting at, which is now you can just flatten these into a sequence, and you can learn this essentially language model to now produce these image tokens given the previous ones. Okay, so now you can learn this kind of autoregressive model, and now it's not producing pixels, it's now producing these kind of latent discrete tokens. Then, suppose that you have this language model, you could then, generate the sequence of discrete tokens. You could then send it to the decoder, and then you've now produced an image. So that's the basic idea. Okay, here again, they're going to change the objective in order to train the encoder and decoder, and it's going to be based on GANs and some additional losses. So maybe I won't go too much into detail here, but just really quickly to see if you haven't seen this GAN loss before, then oops, discriminator. Maybe do I have? Oh, I do have enough details here. Okay. So here again, you're going to have this generator and you're going to have the discriminator. So the generator is going to say, okay, let's produce some data given the latent representation. Discriminator is going to say, okay, given some input, is the input real or fake? So you can see here, it's kind of increasing its score if the data is real. So real will be X. And then it's going to try to decrease its score if the input is fake. So this is X hat is the fake thing produced by the generator. Okay, so that's just really quick, just so that you've, seen the kind of rough idea of this. And, GANs was another thing where there's been like thousands of papers about it, and the whole field was about GANs for a while. And then, over the years, the kind of popular paradigm, can shift. Mhm.
Was there no explicit laws for the generator as like a deconstruction laws?
Yeah, that's a good question. So they do have this perceptual loss. So I don't know the details, but they add additional loss on top of this GAN objective. But the GAN objective does force the generator to produce realistic images because it's going to try to fool the discriminator. Oh, I guess what I'm not showing here is one thing will be minimizing this, one thing will be maximizing it. So basically, if the uh, discriminator is trying to push down this probability, then the generator will try to push it up. And that'll basically incentivize it to fool the discriminator.
Wouldn't it maybe just train the discriminator and not the generator explicitly?
So you have to do this alternating optimization. So you have two, yeah, I maybe should have put more details if I was going to talk about this. So you have two different sets of parameters, discriminator and generator, and then you alternate. So given some discriminator, try to update the generator to fool it. Given some generator, update the discriminator. And so that's basically the setup. And then in practice, it's actually difficult to make sure this is stable. And so that was like a huge area of research for a while. Okay, and then yeah, the reason I want to highlight this is because they actually do then, train this transformer, this, basically autoregressive model. Um, and now instead of 3 million pixels, you can represent an image with really 1,000 tokens. Okay, it doesn't have to be 3 million, but still, it's a big compression. And then here's some examples they get, and they're maybe looking, a bit more promising than those previous ones, like with the Pixel RNN. This one looks kind of nice, but they're far from perfect. So to recap, again, we have this idea of a tokenizer and detokenizer, and then we can try to implement it with this discrete VAE or VQ-GAN. And then the last step is, I think someone asked, like, there's still no text in this picture. Well, now the idea is going to be pretty simple. It's going to be, okay, we have these image tokens. Let's just add in text tokens. And so now our vocab, yeah, has both image and text tokens. And now we can just collect data with both text and images and, train the autoregressive model. So what's an example of this? So an example is this DALL-E model. And just to convince you that everything I'm saying is relevant and it's kind of what they did. They again have these two steps. First is we're going to train this discrete VAE, right? It's going to compress the images. And then we're going to train this basically autoregressive model. Okay, they're going to do that by concatenating the text tokens with these image tokens and then, train the autoregressive transformer. So what can you do with this? Now you could say, okay, let's say I have the text tokens followed by the image tokens. Well, then you can have a prompt which says, what do I want to be in my image? You could say a bathroom with two sinks, a cabinet, and a bathtub, and then you generate the image. Here's like I think they were testing some unique combinations. And I actually picked the good examples. They had some failure cases too. Uh, so here's an illustration of a baby hedgehog in a Christmas sweater walking a dog. I think in the failure case, the dog was also a hedgehog, stuff like that. And you can see that if you look at the details, they're kind of crazy. It's like, roughly getting at the idea, but it's definitely far from perfect. So as a spoiler, in the next class, we'll talk about diffusion. And basically in DALL-E 2, they did a comparison between an autoregressive model and diffusion, and they ultimately went with diffusion. And then in DALL-E 3, I think, that's going to be based on diffusion to get the really high quality images. Um, so I think that's all I want to say about this. And then here is the last example. So this is what I was saying before. So then people, various groups might try to scale this idea up. So again, the nice thing about this is that you could possibly really just, keep everything the same in the sense that like we now essentially have a language model and now it just has these image tokens. And so what if we just scale it up? Maybe it'll work really well and we'll have a model that can, generate both text and images. So that's what they tried to do here. You could see nothing crazy going on based on what we've talked about. I think they actually use this VQ-GAN as their tokenizer and detokenizer. Maybe like a slightly, a follow-up to it, something like that. The idea is they collected 10 trillion tokens, so this really was large scale, right? And then they just do pre-training and they make sure the data has, both text and images. So here's an example. What is happening here? So, oh yeah, so here in their prompt, they have this image, right? And they also have text. So this is just showing the idea of taking in both modalities. And then here it's producing response. It produces some text, it produces this image, and then it keeps producing more text. Okay, so in some sense they did, in some form achieve the goal that we talked about at the starting of the lecture, which is, yeah, have a model that could both input and output both of these modalities. Now, so what are some of the trade-offs with this? So again, the pro is that in some sense we've, unified everything. Everything is just this autoregressive model and everything is tokens. Um, I think one con with this is that since we're using this discrete tokenizer, there's kind of two different limitations. One is that the VAE or the VQ-GAN is in some sense not unified, right? It's separate from this model that we're training. You have the separate tokenizer and detokenizer, which is like a learned model. Then you have your generative model. So that can get, in some sense, that's not unified. And then in particular, you're going to suffer this kind of information loss. So this is actually from the Dolly paper. And here maybe they were trying to say that there's not much information loss, but maybe I'll interpret it differently, which is if you're really, really trying to have really high quality images, then you're gonna run into issues. Especially here, you could see a lot of these details are getting dropped. In this kind of synthetic example, that there's cases where a lot of the structure is getting dropped, and that's again because you have this kind of bottleneck of um, the autoencoder. Okay, so I'm not saying it's not possible to try solving these issues. But in the next class, we're going to take a look at the diffusion models, and those are going to lead to just a different way of doing things, and you can get kind of like state-of-the-art image generation results. Now, with those, it's going to be trickier to kind of generate text with the diffusion model. Okay, so we actually managed to get through everything today. Again, here's just the overview. And again, next time we're mostly going to focus on things that are just generating images. Maybe since we have some extra time, let me see if there's any questions I can answer here. Mhm.
So like even like the state of the art models have like a lot of trouble generating text
Mhm.
on images.
Mhm.
And like given like the amount of like sort of text-based processing that's happening with like in the background, like why is it still like sort of like is it like the same pipeline for like text on the image? And it's just sort of be constructed by the order here versus like sort of generating text separately.
Mhm.
So putting it on there.
Yeah, that's a good question. So the question is like if you're generating text in the image, A lot of methods struggle with that. So yeah, that'll be a whole like issue to try to tackle. Maybe I can look at some of the methods and try to incorporate them into the next lecture. I would say with the autoencoder based method, I think there, text is very information dense. And so your latent representation would have to preserve all of the information needed to reconstruct all of the text. And so definitely with the discrete VAE, it's not clear how to do that, right? Because you basically have to represent all the text in the image as these small number of tokens.
So like the reason why like the models we talked about today struggle a lot is just text is like a lot of information dense in general.
I think that it seems like a plausible reason because it would have to use a lot of its kind of latent capacity just to represent the text. So then if you also have really high diversity of images, then maybe the kind of latent bottleneck is would lead to information loss.
Or like the chameleon models isn't like text generation like literally happening in the background. So I don't really know.
Yeah, so here, um, I guess I thought you were asking about like inside of an image if there's a lot of text. Yeah. Yeah, so mhm. Oh yeah, because you're gonna have separate tokens in your vocabulary still for text. So you're gonna have your image tokens, and then you're gonna have all of your BPE tokens for text. And so the generation of text is yeah, a separate tokens than the images.
You can combine.
You uh no, because the image tokens are image tokens because there's a decoder that can produce an image from them. So you'd have to train your decoder. Yeah, yeah, yeah. Yeah. Okay, any other questions? All right, thank you for your attention, and I will see you on Tuesday.